All right, so let's pick up then with reaction rates. And so the bulk of what this chapter is going to go over is just this. Not only looking at reaction rates in terms of, well, this might make it a little bit faster or a little bit slower, but actually getting into quantifying it. And so here we're going to get our first real taste of some of the calculations that are involved with this. And so when it comes to reaction rates, depending upon what the chemical reaction is that we are monitoring, we can look at the rate of reaction one of two ways. We can track the reactants and mark how quickly the reactants are going away, how quickly they're disappearing. Or we can monitor the products and look at how quickly the products are appearing. And what we are going to find is that the rate of reaction that exists, whatever it is going to be related to one of those two factors. And you can actually figure out the other factors using stoichiometry. So those skills that we built in Chem 105, we're not going to use them directly here. I'm not going to ask you very often how to convert grams of sulfur dioxide into moles of sulfur trioxide product. But some of those concepts are going to cross over and carry over. And this is one of those places where it will. Now, as far as rates of reaction are concerned, what we can look at here is we can look at, let's presume that this is a 1 liter container. If this is a 1 liter container, then the current concentration of A, just so you know, when we put a substance in brackets like this, this is going to refer to its concentration in molarity, moles per liter. You're going to see this a lot throughout this semester. But the concentration of A, which is our reactant here, is 1 mole of A over 1 liter, or 1 molar A. And B, since we have none of it, its concentration is going to be 0. At the 20-second mark, those concentrations go to 0.54 molar for A and 0.46 molar for B. And by the time we get here, it's 0.3 molar for A and 0.7 molar for B. Now, in terms of rates of reaction, this is where we're going to have to do some division. The rate of reaction would be the change in concentration divided by the change in time. And so again, we can look at this from the perspective of each one of them and make those calculations. So let's just say that we are looking at the change in concentration for the product B. Well, that would equal the change in concentration for B divided by the change in time. We could do that calculation by looking at the concentration at a given time and at a second time, and comparing the two times that were there. We call this an average rate of appearance, because basically what we are doing is we are taking the average of that time frame, whatever it was. So in the case of B, looking back again where we were, we started at 0, we ended at 0.46. So 0.46 molar minus 0 molar over 20 seconds minus 0 seconds. That'd be 0.46 molar over 20 seconds. Put the end of the calculator real quick. We would get that this average rate for this time scale is 0.023 molar per second. So in that 20-second window, roughly 0.023 moles were generated every second. So this is our first kind of calculation, the average rate of change. And all we have to do for an average rate of change is just this. Take whatever it is, look at the two concentrations, the two timestamps, subtract them from each other, and divide the concentration by the time. We could do something similar for A, looking at the changes of concentration in A versus the change in time. Looking at that same 20-second time period, we know that we were at 0.54 molar at time 2 and 1 molar at time 1. And so if we do the math out here, what we get is that A has a rate of change of negative 0.23 molar per second. Same calculations, same everything. Why is this one negative? Well, because this is a disappearance. B was appearing, so its concentration was getting higher. A is disappearing, so its concentration is getting lower. Now, if I compare the two, I should notice that quantitatively, it's the same value. B increased by 0.023, A decreased by 0.023. Where does that come from? Well, it comes from that balanced chemical equation. The stoichiometry of that equation says that it's a 1-to-1 ratio of the two. So what does that mean in realistic terms? It means that A disappears just as fast as B appears. So like I said, it's not a direct application of stoichiometry, but it's an indirect one. That balanced chemical equation tells us the relationship between the two factors. Now, if I wanted to set them equal to each other, notice that there's this extra negative sign here on the disappearance. That's so that I can equate them. If I want to use the rate of disappearance to figure out the rate of appearance, I've got to flip the sign to make them equal to each other. And vice versa. If I want to take the rate of appearance and figure out the rate of disappearance, I've got to flip the sign in addition to applying whatever stoichiometry I need to apply. And so that's why we've got that extra negative sign here in the calculation, here in the formula. It's not a mistake. It's there's a sign convention so that we can actually link those two together, and we don't actually need data on everything to do the calculations that we want to do. In reality, if I have a balanced chemical equation and one rate of change, I can figure out all the other rates of change using stoichiometry and the sign conventions. So let's look at a real example. We're looking at the synthesis of nitrogen monoxide from its elements. Nitrogen reacts with oxygen to make nitrogen monoxide gas. Well, if I look at this reaction rate, I can see that the reaction rate is going to be equal to the opposite of the rate of change of nitrogen. So negative, because nitrogen is a reactant and it's going to be disappearing. If you're unfamiliar, the Greek capital letter delta there indicates a change. That change is always calculated as final minus initial. So take final and initial to be whatever you want them to be. You can think of it as later compared to earlier, first compared to last, however it works. But what we are comparing there is we are looking at the change in the concentration of nitrogen compared to the change in the time. And from a calculation standpoint, all we would need are the data at two given points to give us that reaction rate. So what if I wanted to look at the other factors? So we started with nitrogen. Nitrogen, change in nitrogen over change in time. What if I wanted to look at the rate of change of oxygen? Well, then it would be simple. The rate of change of oxygen would be the same as the rate of change of nitrogen because stoichiometrically speaking, they're the same thing. It's a 1-to-1 ratio of nitrogen to oxygen in this balanced chemical equation. And if I wanted to look at the rate of reaction for the nitrogen monoxide, well, stoichiometry tells me it's double. Nitrogen monoxide is going to be coming out twice as fast as nitrogen and oxygen are going to be used up. Where it can get a little confusing for us is looking at how does this doubling turn into a 1/2 in our comparisons. And the answer there is actually pretty simple. When we are calculating rates of reaction, we are looking at it from a perspective of singularity. If I have one molecule of something that is reacting, what is the rate of that reaction? Or if I have 1 mole of reaction, what is the rate of reaction? Rates of reaction, rate laws are always calculated that way from a singularity kind of standpoint. And so if our reaction coefficient is double or triple or whatever, we have to understand that that is going to be double or triple or whatever the actual rate of reaction. And that's why we have to take, if I'm looking at it from this perspective, if I'm looking at it from the perspective of the rate of change of nitrogen monoxide, that's why I have to cut it in half. To make all of these equal, I have to cut the nitrogen monoxide reaction rate in half because it happens twice as quickly. Otherwise, I can't get those three to be equal to each other. So negatives for reactants, positives for products. And if we're comparing rates of change to each other, whatever the coefficient is, we have to factor that in into making it correct. Now, that said, if I know the rate of reaction of nitrogen, and I'm asked to find the rate of reaction for the nitrogen monoxide, your instincts about doubling it are absolutely correct. That's exactly what you need to do. Because if I'm just comparing the rate of change for one reactant to the other, I just use my rules of stoichiometry to do it. But if I'm looking for something else, if I'm given the rate of reaction instead of the rate of appearance or disappearance, I have to understand what that means. I have to understand that rates of reaction are all distilled down to a coefficient of 1. And so if I know my coefficients, then again, it just becomes a matter of applying the correct stoichiometry. But if I need to take this rate of change for nitrogen monoxide and turn it into a rate of reaction, I've got to divide by that number. I've got to divide by that coefficient to turn my rate of appearance into a rate of reaction. Because I've got to get that bottom number, that denominator, down to 1. So more generally speaking, again, if I'm looking at things from a standpoint of reaction rate, the rate of the entire reaction, as opposed to the rate of change for an individual reactant or an individual product, then it becomes a matter of whatever that coefficient is becomes the denominator of my fraction for it. And if I'm looking at rates of disappearance, I need to make sure to take the opposite sign because my rate of reaction cannot be negative. It has to be positive. But more often than not, we're usually being asked to do calculations comparing one reactant to another, one substance to another. There will be times where we have to calculate rates or use rates, and that's where this will become important. But I want you to think things more broadly. in the scope of that stoichiometry kind of idea. All right, questions so far? All right, let's look at this sample exercise then. Each year, roughly 130 million metric tons, that's 1.3 times 10 to the 11th kilograms, of ammonia are produced worldwide, mostly for use as fertilizer. Process for making ammonia is based on the reaction nitrogen plus 3 hydrogen equals 2 ammonia. How is the rate of formation of ammonia related to the rates of consumption of nitrogen and hydrogen? So to answer this question, if I am looking at the rate of formation of ammonia, so that'd be delta concentration excuse me, delta concentration of ammonia over delta time, if I'm looking at that as a comparison, just comparing them to each other, I can use stoichiometric factors to do that. So from that standpoint, if I'm looking at the rate of change of nitrogen over time, I know that the nitrogen would be the opposite sign. And the stoichiometric factor would be 2 ammonias for every 1 nitrogen. In other words, the rate of disappearance of nitrogen is going to be half of the rate of appearance of ammonia. Again, that makes sense in the context of the balanced chemical equation. The ammonia is going to appear twice as fast as the nitrogen disappears. Also in context, if I'm looking at the rate of change for hydrogen over time, again, it's going to be negative because it is a reactant. This time, 2 ammonias for every 3 hydrogens. We're going to see that the hydrogen is going to disappear 1.5 times faster than the ammonia appears. So again, stoichiometry is going to be our friend in this one. All we really are doing is, if we think about it in terms of one of those mole ratio things, I had moles of ammonia in the numerator, so moles of ammonia go in the denominator, that's why the 2's are there. Moles of the reactant go in the numerator, that's why the 1 goes there and the 3 goes there. So that's one way to look at it. If we're just comparing those 3 to each other, that is what we would do. And so if I was given the rate of formation of ammonia, I could cut it in half to get the rate of disappearance of nitrogen. I could multiply that by 1.5 to get the rate of disappearance of hydrogen. Now, the other possible question, not asked here, but could be asked in the future. How are all of these related to rate? And that's where we have to do one of these things, where we put all of the coefficients in all at the same time. If we do that, the rate of the reaction in total is equal to the opposite of the rate of change of nitrogen over the change in time, or 1/3 of the rate of change of hydrogen over change in time, or 1/2 of the rate of change of ammonia over time. So all we're doing in this second one is, if we're relating them to the rate of reaction globally, we're just looking at putting that coefficient in the denominator of that fraction. So what we do with this information really is based upon what we're asked to do and what information we are being given. All right, any questions with this example? So this comes back to an idea that I've been kind of hinting at, but I want to make sure that we state explicitly. Let's say that we are given two rates of reaction. We're told that the rate of appearance for the ammonia is 0.472 molar per second. We're told that the rate of disappearance for nitrogen is negative 0.0236 molar per second. If we were asked which one should we use to give us the rate of reaction, the answer to that one is this. If one of these is expressed in the balanced chemical equation with a coefficient of 1, that's the one that we should use. If not, then we just do our best. We convert by dividing whichever one we want to do. So in this particular case, we know that the rate would be equal to 0.0236 molar per second. Again, since the reaction is this. So if I'm asked to qualify what is the rate of reaction for a given reaction given all of these different rates of appearances and disappearances, the easiest trick, the easiest rule of thumb is just to pick the one that has the coefficient of 1. And if there is no coefficient of 1, pick one of them, divide it by the coefficient that it is. So if I wasn't given let's say that I wasn't given this value here. I was only given the ammonia. Well, if I take that value and divide it by 2, which is the coefficient of the ammonia, I get the 0.0236. So it really just comes down to what do you have What are you looking for? So thus far, we've been talking a lot about average rates. I got data at this point and data at that point. I can figure out the average rate of appearance or the average rate of disappearance between the two time points. And a lot of times that's good. And that's good enough. Problem is, sometimes that is what our reaction actually looks like. So let's say that we are monitoring the reaction between this butyl chloride and water to make butanol and hydrochloric acid. Well, we can see that this isn't a linear function. The rate of change isn't consistent. And so depending upon what part of the reaction you use, you're going to get different results. And you're going to get different average rates of change. And that can be problematic for us, because what if I need a very specific value? Well, to help with that, we can do what are called instantaneous rates. Instantaneous rates involve the use of tangent lines. Now, if you remember back to trigonometry, a tangent line is a linear line that touches exactly one point on a graph. And for those of you that are kind of calculus-minded, tangent lines are also related to individual changes in slope. That's where we can get into derivatives and other kinds of calculus-based manipulations of graphs. So instantaneous rates can be found using tangent lines like these. Now, what do you do if you are giving graphical data and you don't have the ability to calculate the tangent line at that part? Well, the simplest trick to work around it is, if you are collecting a lot of data points, pick the two data points that sandwich it, and you can get a relatively good estimate of the instantaneous rate. Calculating the average rate of those sandwich points, you can get kind of close. And I know in your might be in tonight's post lecture, it might be in the homework, you'll probably see a question or two that is like that. That's what you're being asked to do. You don't actually have to calculate the tangents and get into the trig and calc aspects of it. You can go straight to the source. You can just, there are usually enough data points in there that you can estimate it pretty well by taking the average rate in between. So where this is going to become important for us is here. Instantaneous rates at time is equal to 0 are going to give us what is called an initial rate of reaction. That initial rate of reaction is going to be the one that we focus on the most, because as you can see in this graph, this is pretty common, reaction rates slow down over time. And so giving us information about initial rate is kind of the most accurate depiction of how quickly the reaction goes and how the things that we are manipulating actually impact the reaction itself. So we'll get into more of that kind of stuff tomorrow, but here's kind of a sneak peek at it. That's ultimately what we're going to use to do some of these calculations tomorrow. And it's exactly for that reason. Reactions slow down over time. We can clearly see that if I look at the tangent line up here at time equals 0, compared to the tangent line here at time equals 600, the slopes of those lines are nowhere near each other. The rate of change up here, which would be the slope, is way, way bigger than the rate of change here at time 600. Again, thinking about things from getting into a pseudo-calculus kind of standpoint, that's one of the places we're going to go as far as derivatives are concerned later on, is looking at how those rates of change. So we're going to be focusing on that instantaneous rate near the beginning because that's going to be where the reaction is fastest. That's where it's going to be the most predictable for us. So overall, we're going to do a lot of work with both of these. Average rates are going to be applied to individual time intervals, and we understand that those change over time. Instantaneous rates give us the actual rate of reaction at that given moment in the reaction itself. And the slope of that tangent line gives us that rate of change. And so we're going to end up focusing at the top of that curve because that's where the slope is going to be the greatest. That's where the rate of change is going to be the greatest, as opposed to later on in the curve because all curves eventually flatten out. And so the longer we wait to measure that tangent, the more alike every reaction is going to look. We're going to see fewer and fewer differences between them. So the other way of kind of thinking about this is kind of our easy calculation. These are the ones that we've been doing. This is the more difficult calculation, instantaneous rates. Like I said, we can kind of fudge it if we have a large number of data points. We can look at the data points that sandwich the one that we're interested in. So if I'm interested in time is equal to 600, I can look at time is equal to 590 and time is equal to 610. Draw a line between those 2 points. And it's not gonna be the exact value, but it's gonna be a pretty good estimate. Calculus isn't a prerequisite for this class. You don't need to be able to know how to calculate those tangent lines, those other things to get through this. Most of the time, this is the kind of information that we'll calculate another way, or it'll be given to us in some kind of way. All right, let's take a look at another example. We've got a high temperature reaction between nitrogen monoxide and hydrogen. The reaction is given in balanced form below it. The initial rate of change for the concentration of nitrogen monoxide is -6 times 10 to the -5 molar per second. What are the initial rates of change in the concentration of the other 3 substances in the reaction mixture? So the way that I would be approaching this problem is looking at it from the standpoint of stoichiometry. Nitrogen monoxide, hydrogen, and water all have the same stoichiometric coefficient, which means they are all going to appear and disappear at the exact same rate. So if the rate of change for nitrogen monoxide over time is equal to negative 6 times 10 to the negative fifth molar per second. Well, I know that for hydrogen, since hydrogen has the same coefficient and is also a reactant, it's going to be the exact same, 6 times 10 to the negative fifth molar per second. And for water, it's going to be the same thing. Only difference is it's a rate of appearance instead of disappearance. So the rate of change for water over time would be equal to a positive 6 times 10 to the negative fifth molar per second. For the nitrogen, well, nitrogen's coefficient is half of that of the others, so its rate of appearance should also be half. So what's half of 6 times 10 to the negative fifth? Well, 3 times 10 to the negative fifth. Not asked here, but could be asked other places. What is the rate of the reaction itself here, given these 4 values? Anyone have a guess? Yeah. When in doubt, go with the coefficient of 1. So that'd be the nitrogen in this case. So the rate of change will be 3 times 10 to the negative fifth molar per second. So again, we can use stoichiometry to convert an individual rate of change to all the other rates of change. If I want to look at the rate of reaction, I have to get it down to singularity. And so that means either picking the one that is singular, that has a coefficient of 1, or dividing appropriately to get that coefficient down to 1. Any questions? All right. So, got a question for you then. Here is the instantaneous rate of decomposition of dinitrogen pentoxide into nitrogen dioxide and oxygen. What I want to know is, what are the instantaneous rates of appearance for the nitrogen dioxide and for the oxygen? All right, let's see how we did. Okay, so again, the key here is looking at the stoichiometry, looking at the relationships between the dinitrogen pentoxide, the reactant, and the 2 products. So the rate of change for the dinitrogen pentoxide over time was negative 4.2 times times 10 to the negative 7th molar. Now for nitrogen dioxide, we can recognize that basically the nitrogen dioxide is doubled. There's twice as much nitrogen dioxide as the dinitrogen pentoxide. So we need to change this negative to a positive, and then we're going to double it. Which would give us 8.4 times 10 to the negative 7th molar. Now for the oxygen, we would have to recognize that oxygen is half as much as the dinitrogen pentoxide, so we're going to do the same thing, but we're going to multiply it by 1/2 instead of by 2. So change for oxygen would be positive, since it's appearing, times 1/2 of the 4.2 times 10 to the negative 7th, which would be 2.1 times 10 to the negative 7th molar per second. All right, any questions with that? All right, so this is our last thing. And we're all on the same page there. All on the same page there. One thing with Top Hat's not really all that great always about recognizing correct responses, so don't pay a whole lot of attention to whether it says correct or incorrect. I'm always going to go through the answer with you. You're getting graded on participation in it, not on accuracy. All right, last thing we need to do today, since this was the last question of the day, we will always end with one of these questions. This is a hotspot question. So on your phone or on your computer, all I want you to do is tap in that picture how you're feeling. Red, this was really hard. Yellow, I need to go through it, but I think I got it. Green, this was easy.